Anyway, so just to review what we had done on this week, we had started looking at this method of images. I mean, if you remember in your first year courses, we had just very simple systems. Now we are slowly moving to more complicated systems, how we can determine the electric field and potential of a more complicated system, such as not just an infinite homogeneously charged plane, but we have a plane plus some charge on it. This, we might ground them. And the basic idea was that these, for example, the infinite plane act like a mirror, so we have this image charge. So we are basically replacing this system with an equivalent system. And both of these systems are identical in the upper hemisphere. Not in the lower infinite space, but in the upper semi-infinite space, they are the same. We did the same thing for a sphere. If we had a grounded sphere with a charge in front of it, we said that out of the sphere, this system is actually equivalent to the system where we replace this grounded conducting sphere by an image charge. Just like in the infinite plane, in the infinite plane also we replace the conductor by a single point charge. Here we replace the sphere by a point charge, and outside the conductor these two systems were identical, and uniqueness theorem told us that that was the only possible solution. Again, of course, inside the conductor things are different. But outside the conductor, in this volume here we have zero electric field. In the same corresponding volume here we have non-zero electric field. They are different. But outside the conductor or outside this region, they are the same. Did we also study the non-grounded conductor? We have a plus Q charge. This time it is not grounded. Did we study this problem? I think we did. So in this case, what we did was, okay, if we put this image charge over here, already this made this conducting surface a zero potential. But then the corresponding charge, the sphere will not be neutral, because when it is grounded, it just attracts charges on the surface from the ground. So it's no longer neutral. This configuration does not correspond to a neutral conducting sphere. So to make it neutral and also at the same time to keep it at an equipotential surface, we also placed another point charge at the center. Let's say minus Q prime if it was neutral. If it had a total charge Q to start with, then we had, of course, Q minus Q prime. So that the charge at the center still just shifts the potential by a constant value on the surface. So it doesn't change the fact that this surface is an equipotential surface. Now, when we are taking these images, let's also look at this problem. Now, this problem, and put some charge over here, we already discussed this problem and we said that, okay, we have three images, but we can also look at it in a different way. We can say that, okay, there will be some charges due to this positive charge, there will be some negative charges here, and some negative charges also on the lower plate. Now, the lower plate will kind of take the image of the upper part, so this problem is equivalent to this problem, with plus Q and minus Q. So we are not only taking the image of the charge, but we are also taking the image of the conductor. And furthermore, this problem of a single infinite conductor is the same as we have these four charges. So we had this plus Q and minus Q, minus Q and plus Q. So kind of in this simple case, at least we could still solve the problem. It also works for 45 degrees. It works for it works for 45, 30. For some special angles, it will work, but it won't work for all angles theta. In this case, it is pi over 2. Now, any questions on the method of images? Well, I was hoping in the homework to map two spheres to an equivalent problem of 2 point charges. That was what I was hoping, but apparently it was wrong. So that's why you were probably having a hard time solving the first question, because you were trying to find spheres, which they are not. Now what you will be doing is you have spheres, cylinders this time. You will show that if you have two infinite wires, the equipotential surfaces are cylinders. That will be your homework. And since the equipotential surfaces are cylinders, if you have cylindrical objects, you can just replace them by infinite wires. And by the way, about the homework. Okay, this homework is postponed for Tuesday, and my proposal would be to distribute the homeworks on Tuesday and take them back on Tuesdays from now on. I think one of the problems is you are getting the homework on Tuesday, so it's just new. There are still 7 days to the homework. You don't start doing it the first few days, then it's the weekdays, and you have all the other lectures. But hopefully, if I collect it on Tuesday, on Friday, you will start feeling the pressure to prepare it, so you will have the all of weekend. Also, you have probably received the email about the exam. The exam will be in P5 downstairs here. At 9:30, you will have 3 hours. You will have the equation sheets, so you don't need to memorize the equations. If there is some equation that you want, I will just give it up. I mean, I don't want you to memorize equations. If I don't give them, that means I'm expecting you to drive those results. It will be mainly an application of the techniques that we will learn here. Any questions before we start the new topic? Okay, so method of images are nice. They allow you to determine the charge distribution of the electric fields and also the charge distribution of more complicated geometries. You can even combine, let's say, a plane with a sphere. Even this problem you can solve with the method of images. So you can just replace this infinite plane. Let's say in this problem, what you will do is you can just replace this. This system will be equivalent to, if you have some point charge over here, due to this infinite plane, it will take the image of that point charge and also the image of the hemisphere. So the sphere will become a complete, total sphere. You have the plus Q charge and the minus Q charge over here. Now it's the problem of a sphere with 2 point charges. Well, each one of those point charges will have their image charge. So these will be corresponding images, and you are done. So this is a much more complicated system than infinite plane or a single sphere, but it's still doable with a method of images. At the next level of complexity, let's say the problems that not all of them you will be able to solve using the method of images, or for example, let's do an example. Let's assume we have a semi-infinite plane. So it starts from here. It's an infinite plane, but a semi-infinite one. And another semi-infinite plane. So it's just like you have these two semi-infinite planes, but on one hand, they are just, you just have this. It's like you take a plane, you bend it over itself, giving a thickness, a separation. Let's assume that these one side is isolated from the semi-infinite parts. Of course, they all go to infinity in this direction, they go to infinity. In this direction, they go to infinity. They're just end over here. And let's assume that the upper plate is grounded. Lower plate is also grounded. So if we would also ground this plate, then the solution is again trivial. the zero potential everywhere satisfies the boundary conditions and satisfies the Laplace equation inside. So let's just complicate it slightly. Let's assume that this side has the potential Vy. So this is my x-axis. This is my y-axis. And the z-axis goes into the screen. Well, there are no apparent charges, no point charges that we put, so it doesn't make any sense to talk about the method of images here. Now what? Well, first thing, remember we are trying to find the solution phi, let's call the potential phi, x, y, and z. You see, if you look at this problem, nothing depends on z. Well, that will kind of simplify our life. So we will just assume that, so since nothing depends on z, none of the potentials on the boundaries depend on z, we don't have any charge anywhere, charge density doesn't depend on z, zero doesn't depend on z. So the potential, there is no reason for it to depend on anything else, on z. It can only depend on x and y. So the potential will be a function of x and y only, not of z. If we would, for example, consider a cube, then of course there will be a z dependence. We will make one more assumption, that this is a function of x multiplied by a function of y. We will see that it will not work for our final answer, but eventually we will be able to get our solution using such solutions. For the time being, it's just an assumption. In fact, this is where the name comes from. We are separating the variables. Now, we know that the potential satisfies the Laplace's equation. Now, if we are taking the second derivative, then only this function depends on x, the second derivative with respect to x. So we have y times the second derivative of x with respect to x. When we are taking the derivative with respect to y, only this part of our solution depends on y. So we have x d squared y divided by the second derivative of y. Nothing depends on z. So this combination should be equal to 0. Now let us divide both sides by x times y. So the left-hand side is 0 divided by x times y is 0. The right-hand side becomes 1 over x. This x is the function x. The derivative of the function f(x) with respect to its argument, plus 1 over function y, derivative of y with respect to y squared. And no matter at which point we evaluate this combination, it should be 0. Of course, at every point in our region, so we have a region where we are trying to solve for the potential. We are trying to find the potential in this region. At every point in that region, this condition should be satisfied. But you see, the first part over here depends on only the coordinate x, whereas the second part depends only on the coordinate y. Now, if I consider different points might have the same x, so this doesn't change, but different y. But this equation should be satisfied for all those points, although they have the same x, but different y. That basically tells me that since this is constant for those points that have the same x, as I change y, this shouldn't change. This should itself be a constant. But if this is constant, a constant times this one should be 0. That means this also should be a constant. Such that the sum of those constants should be 0. Now let's look at the possible solutions of these equations. You see, both of the equations, they are just like, we have the second derivative of a function times 1 over that function is equal to a constant. Two cases will be important for us. This constant can be positive, or that constant can be negative. So let's say constant positive. Then we can write that constant, case 1. We can write it as the square of some real number, because it's positive. So we have the function f should satisfy this equation. And the solutions of this equation they will have this form. Now, since this is just the k squared, I will assume that k is positive. So if you look at this function, since k is positive, as x goes to minus infinity, it diverges. X goes to plus infinity, this term diverges. So, and as it will have such a shape. Assuming a and b are positive, of course. If a and b are positive, it will look like this. If one is positive, the other one is negative, it will look something like this. Let's say this is if a is negative. No, sorry. So if this is x, this is f, if a and b, they are both positive, it will look something like this. Let's say if a is negative, then as x goes to minus infinity, it will go to minus infinity. So it will look something like this. This is when a is less than 0, b is larger than 0. Now the important thing about this function will be, if a and b, they are both positive, it never goes to 0. That is what will be crucial for us. If a and b, one is positive, the other one is negative, it will go through 0 only once. So basically this function can go to 0, can become 0 only once at most. It cannot be 0 twice. Now why that will be important? You see, we have these solutions. We have these equations that the parts of our potential satisfies phi. But you see, phi should be equal to 0 when y is 0 or y is equal to a. Because phi is 0 at those planes. It should be 0. So the solution for y should take the value 0 twice. But that means that for the equation of y, this constant over here cannot be positive. It has to be negative. Now, what happens if the constant is negative? Then we have 1 over f, the second derivative of f with respect to its argument is this negative constant. Let's now denote it by minus k squared, k being a positive real number, then f is equal to a times cosine kx plus delta. This is the general solution. And it can become 0 as much as you like. It can definitely be 0 twice. So now we have these constraints. Y at 0 and y at a, they both had to be 0. And for that to be satisfied, C1 should be negative, because only in that case the y solution can take the value 0 twice. And for C2, hence it will have to be positive, because C2 is minus C1 and C1 is negative. So let's pick these up. Since C1, we said that it has to be negative, let's call it minus k squared. C2 is plus k squared. I don't know what this k is yet, but for each possible value of k, we will see which values are possible in a moment. For each possible values of k, I have this x and y functions which satisfy the boundary conditions at the top and the lower plane. So y will be equal to a times, well, this a can depend on k, I don't know. We will see. Sine kx plus delta k, ky times delta k, and x will be equal to bk times e to power k x plus ck e to power minus kx, assuming k is positive again. Now, let's look at our problem again. Yes.
Assumption'ları yaparken k'in pozitif negatif değil de k square'in pozitif negatif olduğuna bakmıyorum.
Yeah, k squared is positive. I'm defining this. I have this number, positive number, C1 or C2. That should be positive. Every positive number, I can write it as the square of a positive number.
Yes. Ama her negatif için square olarak yazamayız, yazabilir miyiz? Yani çünkü hani k'ye pozitif ya da negatif dersek, hani square olarak aldığımızda pozitif de olsa, k negatif de olsa.
True, true. But that will be kind of double counting, because my solution actually depends on the square of k, not on k itself. So k and minus k, I mean, we can make that change later on, but that would mean that I can let the sign of k free, but in that case I have to take only one of these terms, either the b term or the c term, because the c term will basically correspond to minus k, the negative choice of k. It is possible. It is not it's not wrong. You just need to pay attention of it. Now let's come back here. Now I had found one possible candidate, let's say, phi of xy, product of these two things. Let's say, and that product is ak sine kx plus delta k times bk e to power I k x, no, this is y, I k x, not I, plus ck e to power minus kx. Now let's see, I still need to satisfy my boundary conditions. I know that this function might satisfy my boundary condition. That is why we chose this solution for the y solution. At y is equal to 0, it has to be 0. X, y is equal to 0. This is equal to ak sine delta k bk e to power I k x plus ck e to power minus I k x. This should be equal to 0, no matter what the value of k I choose. But this basically tells me that delta k should be 0. Of course, I can choose delta k to be pi, But I don't really care if I choose it pi, sine of ky plus pi is just minus sine of ky. And I just move that minus sign to this overall coefficient. That doesn't really give me a new solution. So this basically tells me that delta k is equal to 0 for all k. I mean, there are no conditions. For all values of k, delta k should be 0.
You may ask this one. Why e to the power I k?
Habit. My bad habit. They are exponents, not ik will be just the oscillator solution. There are no oscillations in the x, there are oscillations only in the y. Okay, delta k is equal to 0, so phi now takes this form. Well, I have another boundary. That is the y is equal to a plane. My solution should be 0 also there. At y is equal to a, this is ak sine ky, bk e to power kx plus ck e to power minus kx. This should also be 0. So this, not y, a. Well, this basically tells me that k cannot take arbitrary values. K can only take certain special values. And k can only take values n pi over a. Because if I put n pi over a over here, k times a just becomes n pi. Sine of n pi, whatever n is, it is always 0. And n cannot be 0. N equal to 0 means k is equal to 0. So here I have sine of 0. There is no contribution. So n is equal to 1, 2, etc. Now let us look at one more limit. When I look at x is equal to infinite. You see? Yes.
Why can't attain to n minus values?
Minus n values.
Yeah.
Well, for the same reason. You see, if you take, instead of 5, you take minus 5, you have sine of minus 5 pi over ax. You just take the minus out, so I put that minus sign I will put it in the definition of ak. Here inside, I will be left with sine 5 pi over ax or y. Negative values don't give me a difference function. They are basically the same function with a different coefficient. I keep all the coefficients here. Now x goes to infinity. You see, this is my system. I put some non-zero potential on this side. So that's basically I'm putting some charges over here. If you go to infinity, at infinity what you will see is, well, you will not see that localized charge over there. You will only see two infinite planes at 0 potential. But the solution there is 0. So the potential at infinity, x goes to infinity, should be 0. At least definitely it should be finite. But if you look at this term, you see at x goes to infinity, well, this term goes to infinity. K is positive, remember. This term goes to infinity. So this term shouldn't be there. The potential should go to 0 at infinity. So that tells me that bk should be 0. For all k. Now let me rewrite my potential. Well, bk is 0. What remains is ak times ck. I will just give it a different name. Let me just call it d. And k now I will express it in terms of n. For each value of n, I might have a different value of n, dn. Sine ka times e to power minus kx. No. n pi over a y, n pi over a x. Whatever the value of n you choose, of course there have to be some positive integers. This is a solution of the Laplace's equation, which is 0 at the upper plane, which is 0 at the lower plane, and 0 at infinity. Infinity over there. Still, I have one more boundary, the boundary at x is equal to 0 that I need to satisfy. And for a single value of n, this doesn't satisfy my boundary. But note that, let me write this phi n. Phi of x, y, let me write it n from 1 to infinity, dn sine n pi over a y, e to power minus n pi over a x. Well, this also satisfies my Laplacian, because you see Laplacian is a linear operator, meaning that I can put my Laplacian, if I act phi with the Laplacian, I should put a Laplacian over here. I should act this summation with a Laplacian. But the summation and the Laplacian, I can change their order. I can first act Laplacian on this one and sum the results. But the Laplacian acting on this function is 0, whatever the value of n is. So this is also a solution which is 0 when y is equal to 0. It is 0 when y is equal to a, and it goes to 0 at infinity. So this also satisfies almost all my boundary conditions. Then the question is it possible to choose dn such that it also satisfies my boundary at x is equal to 0? So that is my last boundary condition. You see, we said that the potential when x is equal to 0 should be equal to Vy, whatever that Vy is. But this expression, when x is equal to 0, just becomes equal to n is equal to 1 from 1 to infinity dn sine n pi over a y. So is it possible to choose dn such that this sum is equal to this function over here? Now comes the Fourier theorem. Fourier theorem basically states that, you see, this function is defined in the interval y from 0 to a. And Fourier theorem tells me that any function defined in the interval from 0 to a such that it is 0 on the boundaries, Vy has to be 0 on the boundaries. No, it doesn't have to be 0. Any function, in fact, can be written in this form.
Hocam, yn starts from 1, right? Does it start?
From 0?
Yes.
Well, let's put n is equal to 0. N is equal to 0, k is equal to 0. If k is equal to 0, this is sine of 0 is 0, so phi is 0. Well, that's a solution, satisfying all our three boundary conditions. It is 0 at y is equal to 0. It is 0 at y is equal to a. It is 0 at infinity. Okay, no problem. You can add 0 to this summation. But adding a 0 doesn't make any difference. I mean, n is equal to 0 term will just be give me d0.
And why potential 0 at infinity?
Well, if you look at our problem, you see I have this infinite plane. I have this other infinite plane. Here I put some potential. If you go to infinity, what will you see at infinity? You will just see this plane at 0 potential, this other plane at 0 potential, and that's it. You won't see that plane over there at potential v. You won't see that. So if you have two planes at zero potential, then your potential is zero everywhere. So that's why at infinity we have zero potential. Well, let me look at this one. Sine n pi over ay, sine n prime pi over ay, integrate from 0 to a dy. How would you integrate the product of two sines? We will use some trigonometric identities. This will be equal to cosine n minus n prime over ay minus cosine n plus n prime over ay. 1 over 2. I can just write the product of two sines as the differences of two cosines. The arguments of these two cosines are the difference of the angles over there and the sum of the angles over there. And, well, let's evaluate them. 1 over 2. Are the signs correct? I think so. 1 over 2 minus sine n minus n prime over a, y divided by n minus n prime over a. This is assuming if n prime is not equal to n. So then the cosine will be just minus sine, and this will not be 0. Evaluated from y is equal to 0 to a, minus sine n plus n prime over a y divided by n plus n prime over a y, a. And again, y from 0 to a. And remember, n and n prime, they are 1, 2, 3, so n plus n prime can never be 0. But n minus n prime can be 0, so that's why we have to pay a bit attention to this term. This is valid only if n is different than n prime. Well, you see, this is an integer. When we put y is equal, there's a pi over there. Yes, plus. So when we put y is equal to a's cancel, so I have an integer times pi, and I'm taking sine of an integer times pi. Yes. When I put y is equal to a, an integer times pi, the sign is 0. When y is equal to 0, this is sine of 0 is 0, so this is 0. The same thing holds here. This is an integer. Y is equal to a's cancel, an integer times pi, the sign is 0. In the upper limit, it is 0. When y is 0, this is automatically 0, so sine of 0 is 0. So this is equal to 0. Now, the only thing that remains is what happens if n is equal to n prime. This is equal to if n is equal to n prime. I can still do the same thing. This product of the signs is equal to this one. The integral of this one will be 0. It will be the same. N is equal to n prime. This is just cosine 0. Cosine of 0 is 1. So the integral of 1 time from 0 to a is a. So a over 2. So that tells me that this integral from 0 to a dy, sine of n pi over a y, sine of n prime pi over a y, this is equal to a over 2 if n and n prime are equal, and it is 0 otherwise. Do you agree? Now let's come back. This is what we wanted. This is what we wanted. Well, there is a Fourier theorem which says that it is possible to find dn such that this equation is satisfied. So from there we know that it is, there should exist these dn's. What remains is, what are these dn's? Well, we can use the previous result, just multiply both sides by sine of n prime pi over ay, integrate over y from 0 to a. And that will tell you from 0 to a, v of y sine of n prime pi over a times y. This integral should be equal to, from n is equal to 1 to infinity dn, the integral from 0 to a sine of n pi over ay, sine of n prime pi over ay, dy. We had already evaluated that integral. That integral is nothing but a over 2 Kronecker delta n prime. But that Kronecker delta n prime just tells me that in the summation from 1 to infinity, I should only keep the term n is equal to n prime. So a over 2 times dn prime is equal to, from 0 to a, v of y sine of n prime pi over a y. So given v of y, we know what the n constants should be, and hence we know the potential it's about. So we know what our potential is. Let's get over here. This integral is a over 2 dn n prime, okay? Kronecker delta n prime. I have a summation over n from 1 to infinity. But this Kronecker delta over here just tells me that only the term n is equal to n prime contributes to that sum. All the other terms are 0. So if I only take the n is equal to n prime term, it is just dn prime. A over 2 times dn prime. That is the n is equal to n prime term.
Hocam şu integrali alacağımız zaman sinüs n prime pi over a ile çarptık ya, o Fourier transformdan geliyor değil mi?
Here you mean? In this
Daha da yukarıda en başta integrali alacağınız zaman normalde sinüs n prime pi yok elimizde. Onunla çarparak integrali alacağız.
Well, what I did was, I have these functions in my expression of the potential, sine n pi over a y. I just said, okay, let me study their properties. I have many such terms. I have sine pi over a y, sine 2 pi over a y, sine 3 pi over a y, etc. I just said, let me look at that the product of both, two of them and integrate them. In a sense, what I have actually proven is that these functions are what are called orthogonal functions. They're orthogonal in a sense. Not in the real space, three-dimensional space, but we imagine a function space, a space of functions, And in that space of functions, we can also talk about the inner products. But in that space of functions, the inner product will be an integral, not just an ordinary summation over a finite number of components. So it will be just an integral. So in that sense, these functions sine n pi over ay, we know that every function defined in the interval from 0 to a can be written in terms of these functions. So essentially, these functions form a basis in our function space. Furthermore, we had seen that they are orthogonal to each other, defined with this inner product. Now, with that knowledge, what I did over here is, so here I have a relation, okay, Vy is equal to this one. I have a relation with, I have an equation that contains infinitely many constants. You can say that this is one equation for infinitely many constants, but this equation holds at every value of y, and y can take infinitely many values. So in fact, that is basically an infinitely many equations for dn. Then now I need to find a trick to find those coefficients dn. So I have to do something to my equation that will give me, that will single out one of the unknowns. And I already know them. If I just multiply it with this sign, integrate over y, only one of them in this summation contributes to my sum, and that is dn prime. On the other side, of course, I have this integral. And once you tell me what the boundary condition is, I can evaluate this integral, and once I know this integral, I can just find what dn prime are, and once I know what dn prime are, I know my potential. Now, the trick was basically this one, in this separation of variables. First, assume a solution that is the product of functions of a single variable, not all of the variables, but a single variable only. Once you know that function, put that in your Laplace equation and try to determine those functions. What can they be? So that is what we did. And in this case, they just turned out to be sines or the exponents. Then we tried to impose as much as possible our boundary conditions. We already knew the boundary conditions. You see, this was our equation. So y at 0 has to be 0, y at a has to be 0, and let's say x as x goes to infinity has to be 0. And these are the boundary conditions that we can impose on each one separately. So I impose those conditions on my function, on my, let's say, ansatz or assumption, and I obtain one solution. I obtain possible solutions for x and y and hence my phi, assuming that it is a function of it's a product of functions of a single variable. This is the part that depends only on x. This is a part that depends only on y. But it will always turn out that this solution is kind of arbitrary. There's still this integer n. And whatever that integer n is, my function satisfies the Laplace's equation. And it satisfies the boundary condition that y is equal to 0, y is equal to a, and x is equal to infinity. It satisfies almost all my boundary conditions, except one. The boundary condition that x is equal to 0, this edge over here. It doesn't satisfy my solution. But there are infinitely many solutions that satisfy almost all boundary conditions. If I take their sum, it still satisfies almost all boundary conditions, except the one that I couldn't impose up to this point. Then the question is it possible to choose these coefficients such that not each one, but this sum satisfies all the boundary conditions, including the one at the edge? Well, each term already satisfies most of them. There's only one that I have to impose, and that is the condition that x is equal to 0. But of course, there is a question that we didn't discuss over here. We should be able to find the n such that this sum has to be equal to Vy for the given Vy in the problem. Then the question is it always possible to express this function Vy as the sum of such terms? Then comes into the game the Fourier theorem. So this nice guy, Fourier, proved for us that any function defined in a finite interval, you can always write it in this form. Of course, it has to be 0 at the boundaries. So Fourier already tells me that it is always possible to find this Dn. Okay, that is also great. So basically we are done. The only thing left is, so if it is always possible to find it, we proceed to find it, and then we show that the n's can be evaluated in this form given Vy. So once you know what Vy is, you can evaluate these coefficients Dn and put it over here, and you are done.
In the previous part, why did we multiply sine n pi over ay by sine n prime pi over ay? And why did we take the integral?
Here,
Yes.
because I can. Yeah, basically, I know the answer. Now, the idea is basically to use this concept of orthogonality of functions. Again, if you go back to your Fourier series, you will, and you have probably discussed it already also there, these sine functions, they are orthogonal in the sense of this integral. So that I just wanted to prove that they are orthogonal to each other. That is why I just multiplied two of them and obtained this Kronecker delta. I mean, the trick over here is I have to do something to this sine of function of y such that at the end I should get some Kronecker delta. That is what I want. In the case of the sines, it's just enough to multiply it with another sine and take the integral from 0 to a. If you have some other means, just do something, whatever there is, whatever you can come up with, to this sine such that sine is transformed into this Kronecker delta. That is the idea. Because this Kronecker delta will just let me replace all this sum by a single one of these unknown coefficients. Some other integer.
Niye böyle bir şey gerekiyordu? Yani ikisinde enflasyon. Niye böyle bir şey gerekiyordu?
Well, I calculated.
Gerekiyordu?
No, it doesn't have to be different. You see, this equality is true whatever n and n prime are, as long as they are integers. I mean, so that I evaluated for all of them. Why I take n and n prime as integers? Well, they are the ones appearing in my sum.
Hocam şimdi burada bizim diferansiyel denklem hem lineer hem de homogeneous. Non-lineer ve non-homogeneous olsaydı mı?
Well, don't worry. You won't need to worry about nonlinear equations until your graduate studies. Well, non-homogeneous, that is the Poisson's equation is non-homogeneous. You see, we didn't put any charges inside. I don't think you would like to deal with it yet. In graduate school, you will.
Şimdi hocam hani ilk başta bir toplam sembolümüz vardı. Bu V2'ye bağlı şeydi. Orayı niye direkt integral olarak yazmadık? Yani integrale çevirirken niye böyle bir terme ihtiyaç duyduk? Sin, in prime.
Here. We're here.
Ya evet, hani orada ilk toplam sembolüyle yazdım.
No, you see,
Soru integral'i çeviriyor.
no, hold on. We found the solution, right? What is n? N can be 1, 2, 3, etc. N can only have those values. So I have many solutions, and they correspond to n is equal to 1, n is equal to 2, n is equal to 3. Many solutions of the Laplace equation with satisfying the boundary condition. If n is, let's say, 1.5, then, okay, it still satisfies the Laplace equation, but it doesn't satisfy my boundary conditions. So I don't want that. I only want the integer values of n to satisfy my boundary conditions. So I can only sum my solutions, but my solutions are discrete. They are discrete. I might end up having, let's say, for example, if A was infinite, so I just have this plane at a given potential, I can still do the same thing. A will be infinite. But since A is infinite, K basically takes continuous values. Since K was taking continuous values, my solutions would be continuous, and I should take an integral. I'm summing my solutions. If they are discrete, that's an actual sum. If they are continuous, that's an integral.
Diskrit olduğu için ama lineer kombinasyonu bulmak için mi Fourier serisini
No.
çevirdik?
No, I didn't convert it to Fourier series. It just came out to be Fourier series. You see, what I have done, I don't know about Fourier series yet. I am only assuming that my function is the product of functions of a single variable. That is where I started with. Now, for example, later on we will do another separation of variables, not in Cartesian coordinates, but in cylindrical coordinates. There I won't get Fourier series. I started with this assumption. They are products of functions of a single variable. And then that assumption led me to this solution. I didn't make any assumption up to this point, except then the assumption that my solution is the product of two functions of single variable. Okay, then I came here. Now this function satisfies my Laplace equation, satisfies the boundary condition at y is equal to 0, satisfies my boundary condition at y is equal to a, and satisfies the boundary condition at x is equal to infinity. But it doesn't satisfy the boundary condition at x is equal to 0. But we had this, by the way, remember, note that we had this uniqueness theorem. Uniqueness theorem tells us that the solution of the Laplace equation satisfying your given boundary conditions is unique. Here we find infinitely many solutions, mainly because we didn't yet satisfy all our boundary conditions. We satisfied most of them, but we didn't satisfy the boundary condition at this point yet. Now we have to impose that boundary condition. But I cannot impose that to this function. But I don't really care. I have infinitely many solutions, and any sum of them, I can just take any combination of them, and they will still satisfy the boundary conditions at this plane, and also at infinity. They will satisfy the Laplace equation. So this function satisfies, I take any linear combination. This satisfies my boundary conditions at these infinite planes and satisfies the boundary conditions at infinity. Now comes the last boundary. Is it possible to choose dn such that this solution satisfies all my boundary conditions, including this boundary, this vertical line? And it just turned out that this at x is equal to 0, these dn's are nothing but the Fourier expansion of the v of y, the Fourier coefficients of this v of y. It just turned out to be Fourier series. Fine. I mean, I won't say that. I mean, I didn't look for Fourier series. I'm not avoiding Fourier series. My solution just turned out to be at least this potential at this strip turned out to be a Fourier series. Can I do it? Yes, Fourier just told me that you can write this function as a Fourier series. So those functions dn do exist. Since I know that they exist, what remains is how can I extract them? How can I find the Fourier coefficients? And we can find the Fourier coefficients by using this result. Well, of course, you could multiply this with cosine or, I don't know, square root of n prime pi over y, whatever function you like. You can multiply it and integrate it, but they will not be of no use to you. Because what I'm trying to find is this Kronecker delta. That's what I want to find. And I know that these functions, if I multiply two of them and integrate from 0 to a, I get this Kronecker delta. So that allows me to extract these unknown coefficients dn prime. And once I determine my dn prime using my boundary condition, well, the solution is now unique. There is no unknown left in my solution. Do you want to give a break?
Tabii hocam biz Fourier sine serisini biliyoruz. Direkt yazsak da olur.
Sure. But how can you tell that you need that series? Okay, once you come up to that stage, yes. We are basically, it tells me that this equation over here tells me that I have to write v of y as a Fourier sine series, as you said. Okay, let's give a 5-minute break. Let's meet at 50. Okay? And then we will continue.